Welcome back, friends. Before building machine learning models, it is crucial to understand data distribution and how the features interact. For many machine learning algos, apart from the ones which are based on decision trees, make assumption about data distribution being normal, which is a bell curve, and follows the distribution where 68% of the data is within one standard deviation, and 95% of the data is within 2 standard deviation, and 99.7% of the data is within 3 standard deviation. Apart from these assumptions, machine learning algos, other than decision tree based ones, also make assumption that all the features are on the similar scale. Therefore, before proceeding with machine learning modeling, it becomes crucial to pre-process this data in order to manipulate and fit it as per the assumptions of ML models. And there is the use of data transformations like linear transformations in max scaling, standardization, and non-linear transformations like log normalization, square root transformation, square transformation, and many more. Hi, you're with me Anuradha, and today in this tutorial we will be understanding these different kinds of transformations and their effect on the data. We will start by looking at different kinds of data distribution: normal, rightly skewed, or left skewed, to understand what we need and what transformation is suitable for what kind of data. And then we will proceed with each of these transformation. We will apply on different kinds of data these transformation and look at the effect. And eventually we will be applying the transformation on the unseen data, which is test data. I'm fully excited to code along with you this practically oriented tutorial to walk with you the concepts and implementation of different data transformation. So let's get started. Friends, I'm on my Google Colab notebook, the link to which is available in the description below. I've already imported a couple of libraries and primarily the data set of life expectancy, which is related to the number of years a person is expected to live, and this is the data set which is publicly available and related to particular country and year. The target variable over here is life expectancy, which is again the number of years a person is expected to live, and the corresponding features or factors which are likely to affect the life expectancy. Some of them are population, CO2 emission, forest area, and so on. Since this dataset contains good number of columns, I have decided to create a subset by extracting only 3 or 4 columns over here. As the focus over here is to understand data transformation, and we will not be going into any detailed EDA or ML modeling over here. We will be just understanding how to address data transformations like normalization, standardization, log normalization, and more. So here we have a subset df expectancy underscore sub, which contains these columns: beer consumption per capita, GDP per capita, population of the area, and then the target variable life expectancy. So as a first step towards data transformation, what we have to do? We have to first see how our data distribution looks like. Again, reiterating the purpose of data transformation. At most of the ML algos, apart from decision tree based algos, make assumption about data distribution being normal and that the features are on a similar scale. So we will be looking at our data from a similar perspective. I've also added one more additional data set, which is very small sample data set for height of high school boys and girls, just to indicate how a normal distribution might look like. First and foremost method which we know to have a look at data distribution is describe method. And what is the primary purpose of describe method is to understand the general spread of data and also to draw some conclusion about skewness of data. So if we have a look at the height of boys over here, we see mean and median are approximately equal, which indicates that this is a normal distribution. It's not a skewed data. Again, looking at the variance, standard deviation, it is not very high. That means the difference in the height of height range across different boys is not that great. The minimum height is 59 and the maximum height is 77, which indicates that while the 75% of the data is below 68 of height. So the maximum indicates that there is a possibility of outliers over here. So all in all, since mean and median are almost equal, it should be almost normal distribution. Let's have a look at the expectancy dataset. If we look at these columns over here and let's compare the mean of these. So if I see mean of beer consumption per capita, GDP and population, it is more than the median, which is the 50% of data. So that indicates that it is a positively skewed data. Again, if we look at have a look at life expectancy, we will see that the mean is less than the median and it indicates negatively skewed data. Mean is always influenced by the presence of outliers and it shifts towards the outliers. So if the mean is more than the median, and we can clearly see that there is a presence of outliers over here. So mean over here in positively skewed data is shifted towards right, while in case of left skewed or negatively skewed data, so mean is shifted towards left over here. Let's also see one more method to directly get the skewness of the data, and we have skew method for that. So if I check height skewness, which we have concluded is almost normal distribution, we can see that it is 0.225 and very less in case of girls, which is when the skewness is between minus 0.5 to 0.5, then the data can be considered fairly symmetrical. Let's see the skewness of expectancy. Here we see the beer consumption is 0.5. So positive skewness indicates right skewed or positively skewed data, while the negative indicates left skewed or negatively skewed data, which we have also observed through the describe method. As we can see that the population and GDP per capita are highly positively skewed, while beer consumption is moderately skewed and life expectancy is moderately left skewed. Now we can visualize this through histograms, including KDE plot. Let's see how. So I've already described how to create such kind of plots in my previous tutorial related to EDA. So I'll not be focusing over here how to create plots. Anyways, this notebook is available to you. So I have created 3 subplots, one for the distribution of boys' heights, the other for the population, and the other for life expectancy, to see how a normal distribution, positively skewed distribution, and the negatively skewed distribution looks like. So let's run this. Great. If you have a look at this, we will see in case of height of boys, which we concluded is almost equal to normal distribution, we can see the presence of a bell curve, which is almost symmetrical. That means it has mirror image data on the left and right side of the distribution. Though this is not completely normal distribution, but we also know that the mean over here coincides with median. Let's see what is the mean in case of boys. So in case of boys, mean is 67.16 and median is also around same. So if we see the mean over here is here, and most of the data points lie on this area. Again, having a look at distribution of population, it is very highly positively skewed. As you can see, most of the data is here. So this indicates, this axis indicates the total population, and this frequency indicates the count of population. And this is with regard to each country. So if we have a look at, most of the countries have population within this range, while very less countries have very high amount of population. This positively skewed data is also available in many real life scenarios, like in case of salary, where most of the salaries lies within particular range, but some of the salaries have very high range, and those are outliers. While if we have a look at life expectancy, right? Life expectancy is negatively skewed. Can you figure out what does that mean? That means that most of the individual live a life around 75, while very less individuals do not expect to live below this range. This is a very old data set, so we do not have authenticity, but what we are looking at is whatever is in this data set. Alright, so we can also see this skewness is caused by the availability of outliers in the data set. What are outliers? We will be discussing when we will be talking about handling them, but in general, outliers are those data points which do not lie in the normal range. For example, if on an average a class is getting 65 marks, there is a student who is getting 99 marks, that person can be considered as outlier. Outliers can occur in all the cases here, even in normal distribution. To delve deeper into where the outliers lie, or where the most of the chunk of the data lie, we can make use of box plots. Histogram and KD plot over here is giving us a higher level view of the skewness of data. If we create box plots for the same columns, we will see something like this. As I said, outliers can be available in all the cases. Normal distribution, which is the data points, any data points beyond 3 standard deviation are generally considered outliers. While in case of positively skewed data, you would see that most of the outliers, almost all the outliers lie on the right hand side, and hence it is called rightly skewed data. While in the case of left skewed data, we can clearly see that most of the data points or outliers are lying on the left side. I'll not dive into this for now. I will be leaving this topic about whiskers, IQR, when we will be handling outliers. So just for now, this is how different distribution data looks from the perspective of box plots. Now this was all about looking at the distribution of data for particular columns. And why we are doing this? To identify what all columns need to be addressed to fit into the assumptions of machine learning models. The other assumption which we talked about was the scale of data. Now we will be looking at what the scale of data means. Or rather, let's go back to the describe method. If we have a look at this describe method, we will see that the minimum of bare consumption is 0 while the maximum is 7. In case of GDP, the range starts from 434 and goes till something like so much, right? 1,41,634. While in case of population, the scenario of the range is entirely different, altogether on the different scale. This is the scale, right? Now all of these features have different units, right? And has different range. We cannot compare them one another. But when we need to feed them to machine learning model, which is deriving, particularly the ones using gradient descent or the ones using Euclidean distance like KNN or K, which are working on the distance measures to arrive at the best fit line or to arrive at a similarity between clusters or something like that. we need to have these features on similar scale, and so that we can compare them. And there comes the significance of scale. So this is just to check, although we have checked through describe method that maximum of beer consumption is this and population is this, and so the scale is entirely different for them. So if we again have a look through histogram for these particular columns, beer consumption, GDP and scale population, of course they are positively skewed, but here the purpose is to look at the magnitude, right, which is varying in case of all these three, right? And to compare these, we need to get rid of units and bring them on one single scale so that we can measure them through one single scale. Here, after looking at the distribution and the scales of the feature, we conclude that we need data transformation. And now we will be talking about how to do data transformation. It is crucial to understand that before we proceed for any data transformation step, or in fact for that matter any data pre-processing step, we need to split our data into train test. And the reason is to avoid data leakage. So what is data leakage? Data leakage occurs when information from outside training data set is to create the model. Ultimately our goal is to create the model, and we will be using the data to create the model, and we don't want to influence our model from outside data, right? And test data is ultimately the data where we will be testing the performance metrics of the model. The test data is like outside data or the future data, and we do not want to influence our model with this, and hence to avoid data leakage we need to train test a split data, which I have already done over here. And so if I run this, I have split data into xtrain, xtest with the help of train test split library, and as a target I have taken life expectancy and the independent features as the ones which we have already taken. First we will be taking care of scaling of the features. The scaling of the features can be done with the help of linear transformations, such as primarily called normalization techniques such as min-max scaling, or standardization technique. In some of the tutorials you will see these terms used interchangeably, but these are different. Normalization term itself is quite misleading, as it also talks about normalizing the whole data in statistics, but for now our scope about normalization is min-max scaling technique, and standardization is another technique to scale down data. How these techniques are scaling data? Using different formulas. If we look at min-max scaler, it is using this formula where for given data it is subtracting the minimum value, dividing it with the difference of the maximum and minimum value. Ultimately this brings down the current value of the data x. First of all, if you look at min-max scaler, with the help of this formula we can see that if the maximum or minimum value are lying in the vicinity of outliers, this technique will not help, right? So to apply this technique we need to have data which is not having too many outliers. Coming to standardization technique, what we can see, it uses different formula where it changes the value such that the mean of the whole data becomes 0, right? And standard deviation is close to 1. And to arrive at that, it takes the mean of the data, and then for the given data x, it gives the difference of the data with the mean divided by the standard deviation. This standardization technique is also called z-score normalization, and it assumes, though it is not important, that the data is normally distributed. Now what I am going to do, I am going to apply these techniques one by one, effect on the scales of the data once we apply the technique. Once we import it, we can create the instance of min-max scaler, and then we can apply fit transform method on xtrain dataset. Now let's understand what is fit transform method doing over here. We can also do separately fit and separately transform, while fit and transform is all together doing the job. So what is fit individually doing? It is calculating the required statistics. And what is the required statistics in case of min-max scaler? Is min value and max value. So ultimately the fit is looking at the data and calculating the minimum value and maximum value. And once transform is applied, it is performing this formula on each and every data. So that is how fit and transform is working in min-max. Now once we have this scale data, we can see that it is a NumPy array. And if we want to have insights on this data, we can convert back into data frame. While creating data frame, I can also pass the columns. So if we see over there, this is the scale data. And as we can clearly see, the values have reduced for each of the column. And they are now no more having units, only magnitude. And this can be easily used by machine learning algos which are distance based to arrive at the distance required, or the convergence of gradient descent algorithm is easy. We can also check the minimum and maximum values after scaling. So if we see, the minimum value after scaling is 0 and maximum value is 1, and which was the main functionality of min-max scaling, which said that it will typically bring the data between 0 and 1. So clearly we can see that min-max scaling is solving the problem of different scales of different features. But is it really solving the problem of skewness, which is against the normalized distribution of data by some of these algos? For that, we need to print skewness of the scale data, right? And if I print the skewness of scale data again, I will see that my skewness the same as before the scale data. Have a look at these values, which are the values before we scale data. And let's have a look at these values which are after scaling. As we can see that the skewness remains same, and this can also be confirmed with the help of visualizing the skewness of scale data, which we can clearly see has not changed even after scaling. Although on x-axis we can see this magnitude of the data has changed for the scaled values, right? But we still have to address one problem. Another problem here with min-max scaling, as we discussed earlier, is as it is using maximum and minimum value of the data, and if it has outliers, then it is getting overly impacted by those outliers. And if any of these features has outliers, we cannot compare them, right? So let's move to next solution, which is standardization. As we have already discussed the formula which is standardization uses, we know that instead of using strict upper and lower bound, it uses the data round mean and calculates the number of standard deviation, right? This was the formula. We were fetching out the mean, then applying this formula, such that once we have this data distribution, ultimately it has mean of 0 and standard deviation of 1. We can apply standardization in a similar fashion as min-max scaling by importing a standard scaler, creating instance of it, doing fit transform. Fit in this method of standardization will be calculating the required statistics like mean and standard deviation and applying on the test data, or applying on the data in the form of transform. So we have a data frame, and if we have a look at it again, we will see that if we check the variance, it is now for the standardized data, the variance is same for all the features, right? And if we have a look at the features, these are the values. So there is no limitation in terms of lower value or upper values like in the case of min-max scaling, which was 0 and 1, but the variance is reduced and also the scale of data. And again, the data over here is only having magnitude and no unit. Again, have a look at effect of standardization, okay? Standardization scaling. What we see if we print the value of skewness on standardized data, we will see that the skewness is again same. Again, standardization is not impacting or not addressing the problem of skewness. It's just helping with the scaling down of data, like min-max scaling, but it is not impacted by outliers. And we can confirm the same with the help of visualization, right? Skewness remains same, but if we have a look at the values of x-axis, they have reduced drastically or scaled down. So with these linear transformations like min-max scaling and standardization, we can conclude that we can scale down the data, but we can use only in case the features are not having skewed data distribution. Before proceeding to log normalization technique of data transformation, let's go back and have a look at the relationship between the target variable and the untreated skewed data. For example, GDP per capita. So if I draw a scatter plot between GDP per capita and life expectancy, where I have neither scaled down the data nor rated in any manner, right? We will see this kind of curved graph, or maybe we will find another exponential graph, right? Where, because if you see the scale of the GDP per capita, you will see that the curve is crowded at one place, right? Within particular values of GDP, and scale is not matching, right? And outliers are lying somewhere here, and it is resulting in a curved relationship. So when we apply any algo which is based on distance, such as KNN or k-means or linear regression, logistic regression, neural network, while drawing the similarity to draw a cluster, or while arriving at gradient descent convergence, it will take time, because the influence of the variable which has higher value, right? It will take time and make the algos perform poorly while doing predictions. Let's say if we compress this data from one of the mathematical technique, maybe log, which compresses any data, or maybe square root, what can be the effect? We can have a look by drawing the graph between applying log on each and every data point of GDP per capita and then having a look. If we have a look at this treated data, right, we are applying np.log on GDP per capita. By the way, we are assuming over here that none of the value is 0 before applying log, right? If it would have been 0, this will not work. What could be the treatment we could have done? Either we could have added very small value over here to avoid error, or let's say what we will do, we will see when we are doing actual transformation. But at the end, when we are applying log, what it is doing, it is compressing the values, including the extreme values, and making relation more linear and the distribution symmetrical. This is what is used when we do log normalization technique. Similarly, the other kind of technique to compress the data in case of positively skewed distribution, right? We can square root, right? And when we do square root, we will find this kind of relation. As we can see, this relationship is appearing better and symmetrical and more linear when log treated than the one which is square root treated. So entirely depends on our experiments and problems and type of data, what technique to apply. Again, there is another technique which is square transformation. But square transformation, if you see, we are compressing data over here, right? And more we compress, more the linear relationship we find when we are applying it to positively skewed distribution. Square transformation is more of applicable when we do it in case of negatively skewed data. So let's go directly and apply these techniques on existing our data points. So let's come to log normalization. To apply log normalization, what we are doing, we are importing function transformer from sklearn preprocessing, and within function transformer we are passing this method of np.log1p. So log1p is also taking care of the places where the value of data point is 0. log transform data, we are doing fit and transform method, and now we already know how fit and transform works. And in this case, fit and transform will apply this function on each and every data point of extrained data set. And finally, we have a data frame over here to check the insights. And now if we finally check the skewness after this treatment is done, we can see a lot of improvement in the skewness of data, right? Remember the old skewness, and now every skewness is within 0.5, which is fairly symmetrical distribution. And this we can confirm with the help of our old method of Histplot, and we'll see the distribution has become fairly normal as compared to previous highly positively skewed distribution. And we can see that most of the outliers are also treated with this log normalization, though some outliers are still available in population, and same availability of outliers can be checked with the help of box plots over here, right? So once we are doing log normalization, also one thing to note is that data scaling is done with the help of log normalization, and skewness is also treated, outliers are also treated. If we want to scale down our data further, which is not needed over here, we can use scaling techniques. And if we want to treat outliers, we can use outlier handling techniques, which I will talk in separate tutorial. And similarly, if we apply square root transformation, we already saw that the effect was not that great, and so the skewness is reduced definitely drastically with compression of data, but not as good as log transformation. Again, coming to square transformation technique, where we are using np.square method within function transformer, we will apply it on negatively skewed data. Now in our current data set, we have only this negatively skewed data available, so I will show the effect on this. So we can see this, and after that we can see that the distribution is fairly normal, and the values have scaled up in this case, right, as expected, where that every value is applied, and every value we are squaring the value. So that was all about data transformation technique, and that was all about this tutorial. I hope you had a great insight and will be able to take it forward, the concepts and the practical implementation. If you really like it and subscribe it and share it. Thanks for now.